So let's go back to binary trees, a pretty familiar data structure for us at this point. And we're going to be talking about DFS, which is also a pretty familiar algorithm for us, but we're going to be doing it a bit differently. We know it's pretty easy to implement DFS on a binary tree when you're using recursion, but it's more tricky to do it iteratively without recursion. It's still possible though, and the way we're going to do it is by emulating how the recursive function actually runs. We're going to be going through the 3 common traversals for a tree in order traversal first, which is going to be the easiest one when we do it iteratively. And we're also going to do pre-order and post-order, which is going to be the hardest one when we do it iteratively. So with in-order traversal, we know we're going to start at the root node. And the idea is that we want to traverse the entire left subtree before we traverse this node. When we say traverse, we essentially mean doing some kind of operation on the node. In our case, we're going to do the simplest thing, which is printing the value of the node. So in this case, we would want to print all the values in the left subtree and then print the value of the root node and then print all values in the right subtree. That's the recursive idea. So when we get to the root node, we simply go to the left. We call in-order traversal on the left child. And when we're here, we do the exact same thing. We don't print this node yet. We don't go to the right child. We go to the left child again. And we essentially keep doing this until we can't do it anymore. So here, we're going to try the same thing. Go to the left child. But we see there is not a left child in this case. We reached a null node. What do we do when we reach a null node in the recursive implementation? Well, we simply return, right? So when we return, we're essentially popping back up to the previous node in the stack. In this case, the stack is the call stack, the recursive function call stack. We know we called in-order traversal on this node first, then we called it on this node, then we called it on this node. So when we pop up the call stack, we're going to pop up to this one first, and then this one, and then this one. And when we do this iteratively, we're actually going to do it the exact same way. So let me draw it out. Let me draw what our stack would look like. In this case, it's not going to be a call stack. We're actually going to explicitly declare a stack data structure and then use it the exact same way that the recursive function uses it. So as we start at the root node, before we print this, we know we have to do the entire left subtree. So we're going to save this guy. We're going to save it on the stack. So we're going to push 1 onto the stack. Well, not literally the value 1, but the node that, contains the value 1. But I'm just drawing 1 for simplicity here. Normally we would add the tree node to the stack or a pointer to the tree node. And then when we went to the left child, we did the exact same thing. We pushed 2 onto the stack. And then when we went here, we pushed 4 onto the stack. And then when we finally got to null, we did not push anything onto the stack. There's no reason to push null onto the stack here. We simply popped back up. So we popped from our stack. We saw that we can't go left anymore. That means it's time to print our parent node here. So we pop 4 from the stack, and I'm just gonna, draw out the order that we're printing it down here. So we popped this 4. And after we pop and print this value 4, what does that mean? Well, it means we did the entire left subtree of 4, which was null in this case, and then we printed 4. Now it's time to do the entire right subtree of 4 before we go back up to our parent now. So essentially, we're going to move our pointer from this node to the child node, which is null. So what do we do when we reach null? Well, we simply pop from our stack again. So I'm going to pop this 2 from our stack, print it, and after we pop the 2, we do the exact same thing. We know we did the entire left subtree of 2. We just printed 2. Now it's time to do the right subtree of 2, which in this case, again, is null. So what are we going to do? Exact same thing we just did. We're going to pop from the stack. As long as it's non-empty, of course, which in this case, we still have 1 more value here. So let's pop that guy. We print 1. We've traversed all of these nodes. Now it's time for us to traverse the right subtree of 1. In this case, it's finally not null. So now we're going to set our pointer to the right child and run DFS on this subtree. So what do we do when we reach a node that's not null? Well, of course, we push it to the stack. We're going to save it for now and first do the left subtree. Only after we do the left subtree can we traverse this node, can we print this node. In this case, the left subtree is null. So that means it's time to once again pop from our stack. Thankfully, it's not empty. If our stack was empty, then we would stop. But in this case, we have one more value here. Let's pop 3, print it. Every time we pop a node, we simply take our pointer and then shift it to the right child. In this case, the right child is non-null. So what do we do with a non-null node? We simply add it to the stack. And then we go to the left subtree. Left subtree is empty. We have nothing to traverse here, so we pop from the stack, printing the 5. 5 has been traversed, then we go to the right subtree, so our pointer now is at null. What do we do when our pointer is at null? Well, we pop from the stack, but now our stack is empty. So if our pointer is null and the stack is empty, then we don't have any more nodes left in the tree to traverse. So that's how you know we can stop the algorithm. So maybe this idea of iterative DFS makes sense to you, using a stack the same way the call stack would work recursively. And believe it or not, the code is actually not super complicated either. So this is what the code for that would look like. We have our standard tree node definition, and then we have our in-order traversal. The code is a bit more long than the recursive implementation, of course, but the ideas are actually the same. We're given the root of a tree node, we create our own stack. We set our current pointer equal to the root node, and we continue traversing the tree while our current pointer is non-null or our stack is not empty. If our current pointer is null, that means the current node that we're at is null. But if the stack is non-empty, that means there are some recursive calls for us to essentially pop back up to still. But maybe our stack is actually empty, but we still have some nodes to traverse. That would mean our current pointer is non-null. Then we would execute a couple conditional statements. If the current pointer is non-null, that means we want to traverse this node after we traverse its entire left subtree. So we're going to save this node by pushing it on the stack and then set our current pointer to the left child. And then we're going to simply go to the next iteration of the loop. So how this code is going to run is we're going to start at the root and then just keep going left until we can't go left anymore. So all of these are going to be pushed onto the stack. And then we're going to end up getting to a null child. And then the if statement would not execute. We would execute the else case where we, of course, pop back up to the parent. So we pop a node from our stack, print the value of that node because we know every time we push to the stack, the node is not null, right? That's pretty clear by these two lines. So when we pop from the stack, we know it's not null. So we're going to, of course, print the value. And then we know we've printed that value and we know we traversed the entire left subtree. So we're going to set our current pointer to the right child. In this case, after printing this guy, the right child would also be null. So then the if statement would not execute. We would again execute the else case. We'd pop back up to the parent and then do the same thing, then pop back up again. So we have popped all these, and then we would go to the right child by executing this line. And finally, it would not be null. So then we would execute the if statement, try going left, push this on the stack, try going left. Well, it's null, then pop back up, print 3, and then do the right subtree with this line. It can definitely be difficult to wrap your head around this, but as we run the code, we see it's executing the same way that the recursive solution would be executing. And the time complexity and space complexity are also the same. The time complexity is big O of n because we're, of course, traversing all the nodes of the tree. The memory complexity is also big O of n because in the worst case, if we had an imbalanced binary search tree, suppose these nodes didn't exist, we just had one long chain of nodes like that, we would in the worst case have to push all of these onto the stack. So that's the worst case time complexity. Though that being said, a more accurate way of writing out the space complexity would be to say the space complexity is the height of the tree, because that's really what we're saying here. If the height of the tree is really long because we don't have a balanced tree, that's what the space complexity would be. The ideas behind pre-order traversal are also going to be very similar. We're again going to have a stack, We're going to start at the root, but remember, pre-order traversal means that we print or process the current node before we process any of the children nodes. So we process the current node, then we process the entire left subtree, and then we process the entire right subtree. So how should we do it then? Well, we know that we don't have to push this guy onto the stack. We're going to print it immediately. So I'm going to print 1, and we're not pushing this onto the stack. We're done processing this node, but we do have to push something to the stack. We know we're going to go and process the left subtree immediately, basically. Do we need to push this onto the stack? Probably not, because we can just, go there via a pointer. But we know when this entire left subtree is done, we're going to have to go and print the right subtree. But we're not going to have a pointer from 2 to go to this node. We just don't have that. I guess we could pop back up to the parent if we really wanted to, but we already printed that node. Why would we push it onto the stack? The easiest thing to do while we still have a pointer to the root node, while we're still at this node, we should push this guy onto the stack and then shift our pointer to the left child. So that's exactly what we're going to do. We're going to add 3 to the stack and then move our pointer to the left child 2. Now we're at 2, we're going to print 2. So we print it. Then of course we want to go to the left child, but before we do that, we should take its right child and push it to the stack. Well, the right child is null in this case, so there's no need to push it to the stack because we know we would want to print 2, then print its left subtree, and then print its right subtree before we go to this subtree. But 2 does not even have a right subtree, so there's no reason to do that. We move our pointer from 2 to be to 4, and then we can print 4, and then we see its right subtree is empty. No need to push anything to the stack. We printed this, so I'm going to cross it out, and we printed this. Now we're going to take our pointer and then set it to the left child of 4, but now the pointer is at null. What do we do when our pointer is at null? It's the first time that's happening for us in this case. Well, you guessed it, we're going to pop from the stack. We did all of these nodes. Now it's time to traverse this guy. It's the reason we're pushing this onto the stack in the first place, because from down here, we definitely don't have access to this node, but recursively, this is the exact same thing that would happen anyway. So we pop 3, and now we're at a node. As soon as we visit a node, we want to print it. So we're going to print 3. We're going to take its right child, which is not null in this case, push it onto the stack, and then go to its left child, which now is null. So when we reach a null pointer, we again pop from the stack. And now we're at 5, then we can go ahead and print 5. So that's the pre-order traversal. It's pretty similar to the in-order traversal, just a slightly different order, I guess, in the way that we're pushing to the stack. Let's take a look at the code. So with pre-order, we again have our stack. We initialize our current pointer to the root again. Our loop executes the same way while our current pointer is not null and our stack is not empty. We're going to be traversing the tree. If our current pointer is not null, when we start at the root, for example, we're going to print that node. If the right child is not null, we're going to push that right child onto the stack. But we're not going to process it immediately. We're going to shift our pointer to the left child first. We're going to process the left subtree first. And we're going to keep doing that until we, of course, get to null, in which case our current pointer is going to be null. And then we're going to pop from the stack. So after traversing all these, we would pop up to this guy that we pushed to the stack in the first place. And of course, we'd keep doing this until we have traversed all of the nodes. This is also going to have linear time complexity where we have to traverse the entire tree, and the space complexity is technically the height of the tree, which in the worst case could be the size of the tree as well. Now, post order is a bit more complicated. We actually will need 2 stacks to implement this. And technically we don't need 2 stacks. There is a variation to do it without 2 stacks, but that one goes in reverse post order traversal and then reverses the output, which I don't think is technically correct. So the most correct way to do this is 2 stacks. Let me show you why we need 2 stacks first though. We get to the root node. We know with post order, we want to traverse this node last. We want to traverse the entire left subtree and then the entire right subtree and then traverse this node. If you try to do it with a single stack, what you're going to find is there's no good way to do it. We end up visiting the same node multiple times. Let me show you what I mean. We're at this node. We don't want to process it yet, so what can we do? We can add 1 to the stack. We know we want to go left first, but we also know eventually we're going to need to traverse 3 as well. So we're going to push 3 onto the stack as well, and then we're going to move down to 2. And this is the correct order that the values should be added to the stack, because we know we want to process 3 before we process the root node. That's the idea behind post-order traversal. Now when we get to 2, we want to do the same thing. Push 2 onto the stack and its right child, well, it doesn't have a right child, and then we get to 4. Do the same thing, push 4 onto the stack, then we get to null. Now we can start popping. We pop 4, we can print 4. Should we add the right child of 4? No, because remember, as we were going through every node, we were already adding the right child to the stack. And then we can pop 2, and then we can pop 3. This is so far in the correct order, but now we're going to end up popping 1. How come we can't get to this 5? Well, it's because sometimes when we pop a node, we want to add its right child, but sometimes when we pop a node, we don't want to add its right child. For example, when we pop 1, we definitely don't want to re-add the right child to the stack. So that's where the visit comes in. The first time we add a node to the stack, we're going to mark it as false. It's not been visited yet. The second time we add it to the stack, we're going to mark it with true. It has been visited. The second time we pop it from the stack is when we're going to print the value. So the way this is going to work, actually, we're going to first initialize our stack with the root node 1 and mark it as false. It hasn't been visited yet. So then we're going to pop 1 from the stack. Since 1 hasn't been visited, it was marked with false. What we're going to do is add its children to the stack and then add 1 to the stack again. The order that we add the children in matters because we know we want to do this in post-order traversal. So we want to process the left subtree before we process the right subtree. So what we're going to do is first add 3 to the stack and then add 2 to the stack. And we're going to mark these as false. I'm just going to put an F for false here. And also, let's not forget to add 1 to the stack, because after we process the 2 children, we also want to process the original root, which is 1. We're going to mark it with a T though, because it's already been visited. But before we add the children, we're actually going to add 1 to the stack again. This time though, we're going to mark it with a T for true because it's already been visited. And then we're going to add the children. The order that we add the children matters though, because we want to pop 2 before we pop 3. So first we're going to add 3 to the stack, and then we're going to add 2 to the stack. We're going to mark these both with an F because they've not been visited yet. Now, the way this algorithm is going to work, we're actually not going to be maintaining our current pointer. Every iteration of the loop, we're going to be popping from the stack. We're going to pop 2 now from the stack. It's not been visited before. So you know the drill. We're going to add 2 back to the stack, mark it with a T for true, and then add its children to the stack. First, we're going to add the right child, which is null. I'm going to put an N for null because we are going to add null values to the stack in this case, actually. Added a little bit of room because we're running out, and this null is going to be marked with false. And then we're going to add the left child, of course, which is 4. We're also going to mark that with false. And now we're going to pop from the stack. We're going to pop 4, which was false. We would add the children, and we're definitely going to add those to the stack, but they're both null. So when we pop those null nodes, we're not going to do anything with them. We're not going to add their children because null nodes don't have children. So I'm not going to draw it out here. But after popping its children, we would also pop 4 again because it would have been added to the stack. It would have been added with a T value for true. So after we pop that, we would have printed the 4. So I'm going to print the 4 here. And then we're going to continue now to pop from the stack. We're going to pop the null value. That was supposed to be the right child of 2, but it didn't exist. So we pop that. And now we just keep popping. Now we're going to pop the 2. It has a T value. When we pop a node with a T value, we print it because it's already been visited before. That means all of its children have been processed already. So now we're allowed to print 2. And let's keep going at this point. Now let's pop 3. When we pop 3, we see it has false. It hadn't been visited before. So you know the drill. We're going to add 3 back to the stack over here. Hard to read, but it's there. It's going to be marked with a T for true. It's been visited. Now we're going to add its children. 5 first with false. It hasn't been visited yet. We'd also add the left child, which is null. But I'm not going to draw that out completely because we would pop that null value and do nothing with it. And now we would pop the 5 value and not do nothing with it, but we would add that 5 value to the stack with a T for true. And we of course add its children, but it doesn't have any. So we would end up adding 2 null values to the stack, and we would pop those, and then we would pop this 5. So 5 had already been visited, so this time we print that 5. Notice how it is going in post order. We printed the 4, then we printed the 2, then we wanted to do the subtree, but we had to do the 5 first, and now we're finally going to pop the 3. It's right here, and it has a T value, meaning it was already visited. So we pop the 3, print it, and now finally we just have one value left in our stack. It's hard to read, but it's this 1, and it has a T value for true. That means we finally popped back up to the root after printing all of the descendants, and this was the post order traversal. Now, while post order is definitely the least intuitive in my opinion of the iterative solutions, the code for it is not crazy complicated. Yes, we have 2 stacks. One stack is for the nodes themselves. The other stack is marking which nodes have been visited before. We initialize it with the root node, marking it as false. It hasn't been visited. While our stack is non-empty, we're going to pop from the stack. We know that the stack is going to be the same size as the visit stack. So as we pop from one, we're going to pop from the other. We're going to have our current node, and we're going to have whether it's been visited or not. If that node is non-null, we're going to do some stuff. If the node was null, we do nothing. We can just skip over it. There's nothing for us to do. Then we have 2 cases with that node itself. Either it's been visited before. If it has, then that's the really easy case. We simply take that node and print it. Right? If one had already been visited before and now we're popping one, that means we already printed all of its descendants. There's no reason to do anything with them. All we have to do is now print one. But if that's not the case, if this is the first time we're visiting one, then we have to add some stuff to our stack, and the order that we do it matters. And by the way, this 2-stack approach could also be condensed into a single stack of pair values. So a stack of pair values where one value is maybe the root node and one value is a Boolean for whether it's been visited or not. The reason I did it this way though is it's a little more generic, and it works regardless of which language you're using. This 2-stack approach is pretty flexible regardless of the language that you use. But what we would do is we would take the current node and add it to the stack. We'd give it a value of true. It's already been visited before. But then we'd also add its children to the stack. It's important to add the right child and then add the left child, because then we end up popping the left child first and popping the right child second. That's exactly what we want to do. But when we push these to the stack, we're going to give them a visit value of false, because this is the first time we're visiting them. And it really is that simple. That's what makes this traversal hard. It's simple, but it's really unintuitive in my opinion. Though the space complexity is still the same, yes, we end up pushing and popping each node from the stack twice, but that's still, big O of 2 times n, which is linear time complexity. And the space complexity, is going to be the same. The height of the tree, which in the worst case could be big O of n, even though, yes, we have 2 stacks, it still reduces to this. Probably the most common application of iterative DFS is implementing a, binary search tree iterator, for example, where we're printing values of the tree or maybe fetching values of the tree in order, but we don't necessarily want to go through the entire tree. Maybe we just want to keep a pointer wherever we are at this point. We start at the root, we want to do it in order. Maybe we just want the first 2 values. So then we fetch these 2 values, and then our pointer is here. And then maybe we want to fetch 2 more values. Then we fetch this, and then our pointer ends up over here. That's one application of an in-order binary search tree iterator. That said, when you're allowed to use a recursive function for these DFSs, it would definitely be recommended because they are easier to implement.